So the next example, we're told that during testing of a REN 180 gas turbine, so the REN 180 is a small demonstration gas turbine that's used in schools and colleges. So we're told during the testing that data in table 3 was recorded. So given the station number, the temperature and pressures, and the RPMs. We were told to assume the specific ratio of specific heats is 1.4, and that the specific heat of air at constant pressure, so CP, is 1.005 kilojoules per kilogram per Kelvin. And we're asked to calculate the compressor compression ratio, compressor isentropic efficiency, and the specific energy required to drive the compressor. We're also asked to calculate the compressor slip, but that does not apply for this video. I'll do that in a later video. Okay, so here's our engine. So there's the impeller, there's the combustion can, the nozzle guide vanes, and there's the turbine blades. So we're told that there's a slight mistake there. Yeah, the mistake was the pressure and temperature should have been pointed to here. Okay, so we're told that the pressure at station 2, so station 2 is the compressor inlet, and in this instance, and we're told it's 100 kilopascals at 290 degrees Kelvin. So that's what we have here. And at the compressor outlet, actually should be here, this point here, T3, it is 440 degrees Kelvin and 205 kilopascals. So the compression ratio then is P3 is to P2, so that's 205 divided by 100, so that's 2.05. If we want to get the temperature, ideally, so the ideal temperature, we just cross multiply both sides by T2, and we plug in the values. So T2 is 290, 205 to 100 kilopascals, and gamma minus 1 all over gamma is 0.4 all over 1.4, and that works out to be 356 degrees Kelvin. Okay, so we have our ideal temperature, but what was actually recorded is 440. So our equation for the efficiency of a compressor is the ideal temperature minus ideal temperature of the output minus the temperature of the input all over the actual temperature of the output minus the actual temperature of the input. So 356 here, minus 290 all over 440, so the real temperature minus 290, and that works out to be 44%, which is pretty poor, but this is just an engine that's used for educational purposes. Okay, the next part of the question was to work out the specific work required. So if we go to the steady state energy equation, there is no heat put into the combustion or into the compressor section, so that goes. We're going to assume that the change in kinetic energy and the change in potential energy are negligible. So we disregard them. So the work to drive the specific work required, I'll say that again, the work required to drive the compressor is M times the change in enthalpy. And that will be M times H3 minus H2, so the output minus the input. And that becomes M times CP T3 minus T2. Okay, we weren't given the mass, so we have to neglect that, and when we do that, we get this specific work, so which is represented by small w. So the specific work then it just becomes H3 minus H2, and that becomes Cp times T3 minus T2. When I plug the values in, that works out to be 150 kilojoules per kilogram. Okay, and we'll leave it there. We'll do the last part of the question in another video.